So we're dot and cross product applications. And this is from section 11.3 and 11.4. So we're kind of pulling from both sections. So let's remember we talked a little bit about work before, and we said that work done by a constant force and we'll represent force by a vector. Constant force F acting along a certain direction. Segment from point P to point Q. So the work done by that force is just the magnitude of the force times the length of the magnitude of the vector between the 2 points. So just the force times the distance is what we're talking about. If our force isn't along the direction of motion, so if the force isn't along the direction of motion, I'll draw a picture. We have this situation. So here's our force. Here's our direction of motion. So this is my force vector. This is point P, and our terminal point here is point Q. And it's acting at some angle theta from the direction of motion. So the component of our force along the direction of motion, this component, is just the magnitude of F times the cosine of our angle. So the work done in this case equals the magnitude of F times the cosine of theta. That's the force in the direction of motion, times the distance that we move, the magnitude of PQ. And if I rearrange this, what do I get? Magnitude of F times the magnitude of PQ times the cosine of theta, which is just F dot PQ. So the work done, if our work isn't in the direction of motion, is just the dot product of the force with a vector that represents our direction of motion. The other way that we can think about this, just because we've talked about projections now. F, the magnitude of F times the cosine of theta is the magnitude of the projection of F onto PQ. So that's just the magnitude of that vector projection. So we could also write, and you'll see this sometimes, I like to think about it in terms of the dot product, but we could also say that the work is the magnitude of the projection onto PQ of F times the magnitude of PQ. So sometimes you'll see it represented this way. But the magnitude of the projection of F onto PQ is just the magnitude of F times the cosine of the angle between them. So I'm guessing that this is probably what you see in physics. This is probably more the mathy way of looking at it. But I'm more familiar with this representation. So the work has to do with dot product, and we're going to next semester when we start talking about three-dimensional calculus, we're going to be calculating the work done not in a straight line, but the work done by a force as something moves on any kind of particular path, and that it gets kind of interesting. So questions on work problems, just dot product problems. All right, let's look at a quick example. These should be, when we have these application problems, they should be pretty easy. So we have a force F is 3I plus 4J plus 5K, and it moves some particle from point 210 to some other point 462. We want to find the work. So we're going to represent the motion from P to Q as a vector. So the vector PQ is just going to be the vector 2, 5, 2. And our work is just the dot product of F with this. So the work is F dot PQ, which is vector 3, 4, 5. And we're taking the dot product with PQ, 2, 5, 2. And we end up with 36. Now our units for work, just what's that? From P to Q, 4 minus 2 is 2. 6 minus 1 is 5. What's that?
Then we use the equation to find it not to not find
PQ, the motion vector PQ and the force vector F don't appear to be going in the exact same direction.
Well, yeah. So they're not in the same direction. That's why I'm using the dot product. I'm just taking the dot product of F with PQ, and that gives me the work. So just going back to what we said before, the force in the direction of motion is the force times the cosine of theta, and when I multiply that magnitude times the magnitude of my vector, I end up with the dot product of F dot PQ. So the dot product is what takes into account that they're not in the same direction. That make sense?
Yeah.
Okay. So our units, in international units, our units of work are Newton meters or joules. So our force is going to be in newtons. Usually our distance, our magnitude of our distance is going to be in meters. It could also be in some other units, but the most common units in international units are Newton meters or joules. In imperial units, our units of work are going to be foot pounds. So if this were in the metric system, this would be 36 Newton meters or 36 joules. If we were imperial units, this most likely would be in foot pounds. We could also do in inch pounds or other units, but it's our international unit of length and our international unit of force. Make sense? All right, let's talk about torque, our application of the cross product. So torque is the way we're going to define torque. Let me redraw this. The way we define torque is it has to do with a moment, and we've talked a little bit about moments. So torque is a moment m, and we're going to define torque as a vector of a force about a point. And remember that we said that a moment is a quantity that's weighted by its distance from a point or from an axis. So we're weighting the force by its distance we're weighting the force by its distance from this point. So let me draw a picture, and we will come up with an expression for our torque. So if we have something like so, and we have point P here, and we have point Q over here, and we have a vector going from point P to point Q. And we have a force acting on, if this is some kind of lever, some kind of bar, a wrench, something, we have a force acting on this thing at point Q. So this is my force vector. Our torque is going to be here, and we're perpendicular, we're making a 90-degree angle here, and we're making a 90-degree angle from M to PQ. So if our force is acting at point P or at point Q, our torque M is PQ cross F. And M tells us the tendency of PQ to rotate counterclockwise about an axis along M. So the magnitude of the torque tells us what the tendency is for that PQ, that position vector, to rotate about the axis defined by M. And we're using the right-hand rule. So PQ cross F, and our thumb points in the direction of the torque. So if we think of our fingers pointing in the direction of PQ, and we're crossing our fingers onto the force F, which is pointing in the direction of our palm. Our thumb is going to point upwards, and our torque is going to be upwards. So our PQ, this vector is going to tend to rotate counterclockwise around M. The vector points down, is going to rotate clockwise. So the magnitude of our torque, the magnitude of M is the magnitude of PQ times the magnitude of F times the sine of the angle between the force, the position vector and the force. And f sine theta, and we'll draw a picture here in just a second. F sine theta is the component of f perpendicular to PQ. So only the component of the force is perpendicular to our position vector contributes to the torque. So let's draw a picture. I'll switch pages and I'll draw another picture here. Questions before we move on? So if we have our position vector like so, this is PQ, and this is my force here. This component, if this is a 90-degree angle, this component is the magnitude of f times the sine of theta. There's my angle. So only the component that's perpendicular to our position vector is contributing to the torque. Only the component that's perpendicular produces the torque. Questions? All right, let's look at a quick example using torque. So we push a 3-foot horizontal bar. With an upward force at a 70 degree angle to the bar. If we're pushing with 20 pounds of force, we want to know the magnitude and the direction of the torque. So I always like to draw a little diagram when I'm doing these kinds of problems. So here's my bar. We could think of this, maybe we're changing our tire, and we need to remove a lug nut, and this is our lug wrench, and we set it horizontal and push. We're going to pull on the, so we're pulling or pushing upwards, however we want to visualize it. So we're pushing like so at the end of our lug wrench, and this force is 20 pounds. And this angle is 70 degrees, and our wrench is 3 feet long. We have a good sized lug wrench. So our reminds me, once when I was when I was younger, when I was in my 20s, I owned a Volkswagen van, and I had to replace. That's not funny. So I had to replace one of the rear hubs on the wheel, and there's a huge nut at the end. And there used to be this place in Boulder where you could rent tools. So I rented this wrench that was like 4 feet long to take that nut off. I felt really manly taking it. This huge wrench. All right. So the magnitude of the torque is the magnitude of PQ cross F, which is our other expression for this is just PQ, the magnitude of PQ, times the magnitude of F, times the sine of our angle. So our position vector, the magnitude of PQ is just the length of our wrench. So, the magnitude of our torque is the magnitude of the cross product. So the length of our segment is just the length of our wrench. So that's 3. And our magnitude of our force is 20 pounds. And we're pushing at a 70-degree angle. If we calculate that all out, we end up that we're pushing with about 56.4 foot-pounds. And our direction, what direction, if we push this wrench, which direction is it going to turn? Counterclockwise. So our torque is going to be out of the page. So the direction is out of the page. So the direction of the vector would be directly out of the page. Direction of M is out of the page. So it's going to be perpendicular. Right. So and our wrench is going to rotate. So our lug nut, if this is our lug nut here, our lug nut is going to rotate counterclockwise. And if we think of PQ, our fingers point in the direction of PQ, and our palm points in the direction of F. If we cross PQ onto F, the thumb is going to point directly out of the page to tell us the direction of the torque. Questions on that example? And I just wanted to mention briefly the scalar triple product. We talked about that when we talked about cross products. I just wanted to show an easy way to calculate the scalar triple product if you ever run into having to calculate the scalar triple product. We said the scalar triple product was A dot B cross C. And that's the same as A cross B dot C. And we said this was the volume of a parallelepiped or a volume of a box with A, B, and C as adjacent sides. To calculate this, we can just use the determinants. So if you ever run across some kind of situation where you have to calculate the scalar triple product, it's easy to calculate with this determinant. And I just wanted to show you that just because I'm not sure where else you'd see it. All right, any questions? Things to be careful with on the torque. I think where most mistakes are made with torque problems, the torque problems we're doing would be very easy, are the direction. Just make sure you're remembering how we find the direction. And it's PQ, the direction is PQ cross F. Your fingers point in the direction of PQ of the position vector of the wrench, whatever, the bar that you're pushing. and F points in the direction of your palm. And if you cross your fingers onto your palm, your right thumb points in the direction of the cross product. All right, homework. There you go.